Hey, howdy, everyone. We'll get started. So thanks for coming today. Sorry for switch up of the rooms. I don't know. But today we'll just do another weekly review session. Right, you just had quiz 1, exam 1 is going to be next Friday, during class time. And so next week, we will also have a Wednesday review session. I'll extend it a little bit, maybe like 4:45, 4:30, something like that, until 6. Give you a little bit extra time to ask your questions. And then I'll also do a Zoom review session Thursday night, like 8 p.m. or something like that, 7 or 8 o'clock, that you can do your last minute questions there. And I'll send that link out and that announcement out next week as well. But just know I will have an extra review session before the exam. Other than that, I don't think I have any announcements. I guess quiz 1, right, will be available Friday, so you can review your answers. I think that's a really good place to start for the exam. And then Dr. Altamos in the past has given out a mock exam, so you might have that to practice from as well if she does that again. Any questions for me before we get started? Alrighty, what do we want to see today? What's giving us some trouble? How are you feeling about the material so far? Good, bad, iffy? Where are we iffy? You can say all of it, yeah.
Can go over more of delta G, how to define it.
Yep. So delta G. Can someone tell me what delta G is?
Free energy, right?
Yep. Do we know who is named
Gibbs
after?
free.
Perfect, right. So this is Gibbs free energy. And what does Gibbs free energy tell us?
The amount of energy available?
Yeah, yep. It's amount of energy available. What does it mean in terms of the reaction? Yeah, if it wants to go to the forward reaction, what do we call that if it wants to go to the forward reaction? Begins with an S. Yep, spontaneous, right? This tells us spontaneity. I don't know if I know how to spell spontaneity. Spontaneous. I don't know how to spell that one. Right? We're going to tell us if something is spontaneous or not spontaneous. If something is spontaneous, what is the sign for delta G? It's negative. Yep. This is negative delta G. And if it's not spontaneous, what does it do?
Positive?
It's positive. Yep. Right. So a lot of chemistry is going to be equal and opposite. So if something is spontaneous, oh, that's unfortunate. If something is spontaneous in the forward direction, right, where it's product favored, then in the reverse reaction, it's going to be not spontaneous, equal and opposite, right? So whatever energy it's going to take or release in order to go in the forward direction, it's going to be equal and opposite in the reverse direction. All right, so if the forward direction is spontaneous, the reverse reaction is going to be not spontaneous. So, right, we can have, right, A plus B goes to C plus D, and delta G would be negative here. So that means that D plus C going to A plus B would be delta G is positive, right? If it's spontaneous in this forward direction, then the reverse reaction is going to be not spontaneous. Any questions on just positive, negatives, spontaneous, not spontaneous? Okay, what does the world prefer? Do we prefer spontaneous or not spontaneous reactions? We prefer spontaneous reactions, right? Prefers. Okay. And if we were to have the most ideal condition for a spontaneous reaction, or I guess before I ask that, for delta G, in order to calculate delta G, what is our big equation for delta G? Delta G equals what?
Entropy.
What is the sign for enthalpy? Good. minus delta S. Is there any other component? Where's T? In the middle. Yep. Yep. So delta G is going to be equal to delta H minus T delta S. Okay, this is the big equation. This tells us if something is going to be spontaneous or not, dependent on the delta H and dependent on the delta S. Yep.
Is the temperature absolute?
The temperature is always going to be in Kelvin, correct? So this will always be in Kelvin. Right, so what does that mean about temperature? Oh, sorry, go ahead. Yes, yep. So delta H, this is our enthalpy. This can be positive or negative. And what about delta S? What can that be? That's entropy. Right, and can that be positive or negative?
Yep.
Yeah, right, we can have either negative or positive disorder happening. So if temperature is in Kelvin, what is the sign of temperature? It's always positive. Okay. All right, so this is really important to know. That means that we have two conditions for enthalpy. They can be positive or negative. Then we can have two conditions for entropy. So that's positive or negative there. So what's the ideal condition for performing or having a spontaneous reaction? What does the world prefer for delta H? Do we want delta H to be negative or positive? Confidently. Do you want to absorb heat or release heat? Release, yep. Okay. If we're releasing heat, that means that the energy from that system, right, is giving heat off to its surroundings, allowing for another reaction to happen, right? We can then use that energy in order to catalyze something else. What about delta S? What do we prefer when delta S? Positive or negative for delta S? Positive, right? Right, we prefer the world to be a little bit more disordered. We want more chaos in the universe. The disorder of the universe is always increasing. Entropy is always increasing. So we do want delta H or delta S, excuse me, to be positive. So those are our ideal conditions. If we were to plug this into our delta G equation, we would see that delta G, when it's negative delta H minus T delta S, what do we notice about all of our components on the right-hand side of our equation? They're all negative. So what does that make delta G? It's going to be negative, right? If we had a negative delta H and then a positive delta S that we plugged in, we have a negative minus a positive, right? Which is just a negative plus a negative. So delta G will always be negative here. Right, so if we did numbers, delta G, if this was negative 3.9 kilojoules minus 278 Kelvin times 430 joules per mole, or joules per Kelvin. Right, no matter what temperature we're at for delta G, your delta H and your delta S are negative and positive respectively. but that temperature component's always going to be positive. So delta G will always be negative no matter what temperature you're at. Okay, everyone see that? Questions on that? This is the ideal scenario, right? We're releasing heat and we're increasing disorder. That's a very favorable reaction. Right, there's 3 other conditions that delta G can be. What are those 3 conditions? Perfect, right? So if we can have a negative and a positive, if we have a can have a negative and a positive delta H and delta S, so then we can have the reverse, right? We could be absorbing heat and we can be decreasing disorder. So if delta H is net positive and delta S is negative, when is delta G at at what temperature would delta G be negative? I see a shake of a head, never, right? It's never going to be positive or never going to be negative. Right, so this means this is always spontaneous. This means this is never spontaneous. And if we show that, right, we have delta G, we would have a negative minus a positive times, oh, I'm sorry, this is a positive, times a negative. Right, so going back to our algebra, we would have keep change that turns into a positive plus a positive. Can you ever get a negative in that scenario? Nope. Right, so this can never be negative. This will always be non-spontaneous, no matter what temperature you change it to. Questions on that one? All right, what's another condition? We have 2 more. Which means our last condition is what? Negative, negative. Okay, so at positive, positive, can delta G be negative? Is one of those reactions favorable for the universe? Yeah, which one? Entropy is negative, or entropy is favorable, right? That one's positive. So if we were to plug that one into delta G, we have a positive minus T times a positive. When does this reaction become spontaneous? Right, because we're only changing temperature here. So when does that become spontaneous? Do you want the first portion or the second portion to be bigger? We want the second one, right? So if we have a positive number and then we have a really, really high positive number, right? Because Kelvin's always going to be positive, something like, I don't know, 1,000 Kelvin, right? Then that might overcome the positive from our delta H. And we would have a second negative number that's overcoming that positive number in the front. So this one's going to be spontaneous at high temperatures. We'll give you a caveat, right? That is like relative for the reaction. Sometimes a high temperature might be 100 Kelvin. Sometimes the high temperature might be 1,000 Kelvin, right? It's very dependent on the reaction, but overall, you want the high temperature for a spontaneous reaction when they're positive and positive. Does anyone know of an example of a positive reaction that is spontaneous? So when you take a ice cube out of the freezer and you put it on your countertop, what does it do? It melts. Do you have to do anything to melt it? No. What is the delta H for melting if you go from a solid to a liquid? It's positive, right? If we go a phase change going from solid to liquid, right, you're breaking apart those bonds, you're breaking apart some of those intermolecular forces, that's going to be a positive delta H. But we're going from a solid to a liquid, so what's our sign for our entropy? Is positive, right? We're getting more disordered. The more as we go from solid to liquid, that's a positive delta H, and then liquid to solid, or sorry, liquid to gas is an even bigger delta S, or increase in delta S. So we have a positive for our delta H, a positive for our delta S, but it happens without you interfering. That's a spontaneous reaction. And that's because your delta S is much greater, right, than your delta H in that situation. And it's because your temperature is at the right scenario, right? Your ice cube is not going to spontaneously melt in the freezer because the temperature is too low. But once you increase the temperature a little bit, then your ice cube melts, okay? So that's an example that you can kind of think of. Yeah. The ice cube is absorbing heat. It's taking heat from its surroundings to melt it. Yep. And then, right, if you put it back in the freezer, then it would go back. Right now you're at that lower temperature. It will spontaneously form the solid again. Okay. So that's a real life example of you doing a spontaneous or not spontaneous reaction. All right. So then if we have the negative, negative, what is going to be our condition for delta G there? When is that one going to be spontaneous? Perfect. Right, and for that one, again, that's like a keep change situation. So you have a negative plus a positive. So you want your positive number to stay smaller than your negative number in the front, right? So that you still overall end up with a negative delta G. So the lower the temp, the more spontaneous that reaction is. Any questions on delta G, what that means? Yep. So that would be like if you took water in an ice cube mold and put that water in the freezer, right? Because you're now going from liquid to solid. That's going to be a decrease in entropy, so that's a negative. But you're forming bonds, and so that is going to release heat. Okay, I think that's about as far as we got with delta G so far. Does that help clear up your question? Okay. Anything else on delta G?
Are there like real life examples for the first two?
Yeah. Do I know them? No. I can look them up. Let's see. So, right, easy in terms of like things that'll happen, right? A ball will fall down a hill, but a ball will never roll up the hill. In terms of like delta H and delta S, that's like, meh. But I think iron rusting, I believe, is a negative positive situation. Let's see if the internet gives me anything quick. No, not really. There are plenty of examples. I know the fun ones, right? All right. Yep, yes.
Then it become like kind of offset, so it's like become two gases or it's like becoming more ordered.
I think. You might be right on that one. Let me look at the equation. Yes, so iron rusting is actually going to be the negative one as well. I had that backwards in my head. But that is another spontaneous reaction that like it's at the correct temperature for it to do. Right, but you can never unrust something without putting effort into it. Any other questions? Okay, anything else you want to see today? An example of a negative positive is a combustion reaction. So when you had Right, so if you burn ethanol, which is C2H5OH, that is a spontaneous reaction where delta H is negative and delta S is positive. And then I guess for yeah. And then this would be a positive positive. No, this would be a bond formation. This would be a negative positive. Sorry, negative negative. Because your delta S is decreasing because you're forming a solid, but then you are forming a bond and that's going to release energy. So just a couple more examples. All right, what else?
You go over the third law of thermodynamics.
Yep. All right, so who can tell me what the third law of thermodynamics is?
Kelvin, there's no motion.
Mm-hmm. Right, so at 0 Kelvin, we have no motion. That means all of our things are solid and all of our things are not moving, right? We don't have in a solid, atoms are vibrating back and forth. But at 0 Kelvin, those are not even vibrating, right? Everything is just still. So that means if there's no movement, there's no change in motion or anything like that, that means that we have no entropy. So At 0K, we have delta S equals 0. So that means with increasing temperature, delta S is going to be greater than 0. A little bit more, right? Even if you give it 1 degree of Kelvin, right, it's just going to vibrate back and forth very, very little bit. But, right, what is room temperature? Does anyone know? Say it again. Yeah, about 25, between 20 and 25, right? So if we're at, we'll say 25 degrees Celsius, what temperature in Kelvin are we in? 298. Right, so to go from 0 to 298, we have to give us a lot of entropy. You have to give it a lot of movement. Right, some things are gas at room temperature because their entropy is so great. Some things are liquid. Fortunately, us as humans, we're solid, right? We the stuff that we are made out of is not, you know, super spontaneous, doesn't have a lot of disorder. Right, if you started boiling us, then we might melt a little bit. Right, so as you keep increasing temperature, you're always increasing entropy, which means that entropy for something can never be 0 and it can never be negative. There will always be some sort of energy or entropy associated with the molecule, the compound that you're working with. So, yep. Yes, absolutely, right? So if we have something like O2, and then we have something like, I'm doing quick math, C2H4. We'll do C2H6. Yeah. All right, and these are going to be at 25 degrees Celsius. What is the structure for O2? Does anyone know what that looks like? Yep. And how many bonds does it have? Calling back some 119 knowledge. Oxygen is going to have a double bond between it. All right, so it's going to look like this. And then C2H6. Going to look like this. This is 32 grams per mole, and this is about 30 grams per mole. Right, so they're pretty similar in their weight. Oxygen with its double bond is going to have a little bit less movement and a little bit less rotation because that double bond doesn't allow it to twist back and forth, right? It can really only vibrate back and forth, and then it can move around as a gas, right, as a gaseous phase. And this is gaseous phase. C2H6, on the other hand, right, now has 7 bonds. All of them are single bonds, so all of them can rotate back and forth. Right, it can flip around, it can spin, it can do all its fun stuff. Right, so there's a lot of different movement that's involved with the C2H6. So this entropy is going to be much greater than, I guess, it's going to be much greater than the delta S for O2. Right, this might be like 205. This might be 500. Right, so even though they're at the same temperature, because there's more stuff going on with the C2H6, it has more disorder than the O2.
That's our ultimate say when bonds stretch.
Yep.
Uh,
So, right, you're always sharing that electron between the two atoms. So between oxygen and oxygen, there's no difference in electronegativity, and between hydrogen and carbon, there's no difference in electronegativity, right? So overall, these are nonpolar molecules. However, your electrons are always moving, right? So depending on when you have those London dispersion forces, things might get pulled in different directions. So, right, sometimes maybe this H will be a little bit closer here, and then sometimes maybe a little bit farther away here, right? So you can move back and forth like you're pulling it on a string or a bungee cord away from those atoms. The single bond is a little bit easier to pull back and forth than the double bond, right? Because if you think you had one bungee cord that you're stretching apart for the single bonds, and then you have two bungee cords that you're stretching apart. So it's easier for the single bonds than the double bonds, which gives it even more disorder. Does that help answer your question?
so it's-
There's probably more in terms of quantum mechanics that go into that. I'm a biological chemist. I don't know a whole bunch of quantum mechanics. But I would say that the dispersion forces are the thing behind it the most. Any other questions? Does that help the third law of thermodynamics? Right, so then that brought us into the delta S of a reaction and solving for that. So we can have delta S of a reaction is equal to the sum of the delta S of the products minus the sum of the delta S of the reactants. Do people remember this if when it was delta H? You were finding the enthalpy of reaction. Right, you're going to be given a chart, and you can solve for those delta S's there. So we can do this one together. It's kind of a lot of information. Okay, so here we're going to calculate the delta S for the breakdown of ammonia gas into N2 gas and H2 gas. You're given your chemical reaction, and then you're given the delta S's for those species in the gaseous form. Right, if one of these were liquid or solid, then they would have a different entropy associated with that. Do you want to try this one on your own, or do you want to work through it together? Yeah, we could try it. You can work with the person next to you, talk to people, give you a couple minutes. Yep. Oh, because I didn't write down the right one. No, I was looking at N2 and then gave you the wrong one. Making sure you were paying attention, right? That's what everyone says. And then they're all in the joules per mole Kelvin for delta S.
Is that 180?
130. Okay, I'll give you a couple minutes. I think you should have everything now. And then remember that this multiplied by the moles. Yep. You can assume 1 mole. Like, yeah. Yep. Get an answer for this. What do we get? What's your unit there?
Right.
Which one do we agree with? Okay, we'll do it together. So the first thing that we have to do is what? We have to balance our equation, right? So how did we balance it?
Multiply her, put a 2 in front of the NH3,
Mm-hmm.
then put a 2 in front of the. Oh, never mind. If you don't.
Perfect. Yep. So you need 2 nitrogens and you need 6 hydrogens in order to balance this equation. Okay. So then what is so now before we even do our math, is our delta S negative or positive? just based off of the reaction. What would you predict the sign of delta? Perfect, right? We're going from one gaseous molecule, or I guess two technically, because we have 2 moles of it, to 4 gaseous molecules. Even before we balanced it, we had 1 gaseous thing on the left, we had 2 gaseous things on the right. So we're always increasing entropy, whether we're looking at the balanced equation or not here. So we're predicting delta S to be positive. So when we check our answer, we should make sure that it's positive as well. Okay, so then for delta S, we're going to have the sum of our products. So we need N2 is 191.6 plus 3 times the delta S of H2, which is 130.7, subtracted from 2 times 192.5. Then I get delta S to be 198.7. Okay, and then what units are we in? Perfect. Right, so now we're in joules over Kelvin. So then if I told you, right, that the delta H for this reaction is negative 37.5 kilojoules. What is delta G? How would we solve that?
Plug it into the equation, delta G equals, delta H minus T.
Perfect, right? And we're gonna say at 25 degrees Celsius. So we have delta G is equal to delta H minus T delta S. What are we plugging in for delta H? So we have negative 37.5 kilojoules. What are we plugging in for T?
25 plus 4, 273.
Yeah, so about 298. And what are we plugging in for delta S? 198.7 joules per Kelvin. Okay, so what do you get for delta G? And we'll say delta G in, yeah. Yep, so those definitely matter. So that's why I put it in just like this. So you want to see kilojoules and you want to see joules. You have to change one of them to the other. It doesn't really matter which one you change. I always think of kilo as times 10 to the 3, so I usually solve for it in joules. So what's your delta G if it's in joules? So I got negative 96 712.6 joules, which can be negative 96.7 kilojoules. So then when is this reaction spontaneous? Yep, so it is spontaneous because it's negative. At what temperatures would this reaction be spontaneous? Yes, at high temperatures. It's always spontaneous. So it's also spontaneous at low temperatures. So this will always be spontaneous. I think I gave you a fake delta H too, but for the sake of the problem, it's fine. We're just doing math to do math. Okay. Yep. Yes. Yep, you can do either one. I always think it's easier to plug times 10 to the negative or times 10 to the 3 into my calculator. So I usually change my kilojoules to joules and then convert back to kilojoules if that's what's needed. But it does not matter which one you convert. They just need to be in the same unit. Anything else? How did we determine that? So I gave you the delta H was negative, and then we solved for a positive delta S. So since delta H was negative and delta S was positive, we're in that always spontaneous condition. Technically, we're breaking bonds in our reaction, so it should have been a positive delta H, but it's okay. If you had a positive delta H or a negative delta H and a positive delta S, it's always going to be spontaneous. Just like how it's always increasing in disorder. Yeah. So it's not the most easily explained. But overall, for all of the reactions that are happening in the universe, right? Things are increasing in entropy, things are decreasing in entropy all the time. Overall, your delta S of the universe is always increasing. So it doesn't matter. It doesn't matter if something is like if your reaction has a positive delta S, it's increasing. That means that the surroundings are decreasing. But that means that the reaction has like a higher delta S than the surroundings delta S. Technically, usually those are the same, but just know that overall the delta S of the universe is always increasing. There's always more disorder happening in the universe, and we're never getting less disordered.
Equation, it's never decreasing ever.
For the universe, you could always have a negative delta S, but that's looking at system and surroundings. System and surroundings, you can have a positive delta S and a negative delta S. Delta S of the universe, that's when it's always positive, right? So you can have delta S system and delta S of the unit of the surroundings, right? These can be positive or negative, but delta S of the universe is always positive. Usually when we're talking about like delta S equaling negative delta S of surroundings, then like, yes, those are equal and opposite. But when we talk about the big delta S universe is always greater than delta S of the system plus the delta S of the surroundings. Right, that's macro scale in terms of that big equation at the bottom. This is just looking at system and surroundings on an individual case. This is like net positive. This is the net case at the bottom. Yep,
Then,
yep.
and heat is lost through chemical reactions.
Mhm.
Lost in reverse. What happens when you eventually run out of energy?
Hopefully we're dead by then. No, that I don't know. That's what people with a higher degree than I'm doing is. I don't really know. I don't really know what happens at that point. I'm assuming that the universe can keep on expanding. So then at some point, so universe is always going to be increasing. The heat portion, I don't know. We need to find a new star, I guess. It's a good question. I just don't know the answer to that one. Anything else? Question? Yeah.
So this is right.
Yeah.
Like I'm trying to solve with the equations here and I can't get to the value that you got. I don't want to do it wrong.
Yep. So did you convert 37.5 kilojoules into joules? Yep. So the big thing here is just this one here. I plug this in as negative 37,500 joules minus 298 and 198.7. Yep. So then you just do. Right, you have negative 96712.6 joules, and then for every 1 kilojoule, you have 1,000. So you just divide by 1,000. Yep. Anything else? Do we know where those are? Do you want me to show you where that is? Yeah. Yeah, so I won't post it until like Friday. So for those that don't know, this one. So under the office hours tab here in the center, if you scroll down a little bit past the chemistry learning lab, then you have your SI sessions, and then you have my sessions. So I'll post the recording and then practice problems and the answers. And then usually the notes that I take on my iPad too, for the review sessions every week. So that's where those are housed. Yep.
Do you know if she posts her own practice problems?
She usually does. I mean, I've worked with her for like 6 semesters now, so she usually does a mock exam before all of her exams. This is her first time teaching 120, so I think she's going to do the same thing for that. So you'll have that mock exam, and then that's like the only practice stuff that she gives out for it. So then it's just chemistry learning lab, me, the SI, or the internet.
I feel like the chemistry, the real math questions on your, they were as difficult as quick.
Yeah, and I think the learning lab is so that you get the basic understanding of it, and it like kind of walks you through all the steps. I don't know if I've shown this class, but if you do, one of my favorite websites is CHEM12025. I used this when I was an undergrad. So cryptic home screen, but then if you click that link, it brings you to this. And this gives you a whole bunch of chemistry problems. So we are in, you have to look around a little bit. I think we might be. No, this is more. I can't find what I'm looking for right now. But in any case, you can look around here. I know they have it on here, but we're going to talk about KSP at some point, right? So here's equilibrium, and it comes to a bunch of stuff. If you need a review on, like, we're going to start kinetics next. So you can have a brief introduction of kinetics, and then it like gives you all this information, which I think is super helpful. So you can always pop around that website, and even if you just type in like delta G equations chem team, usually something pops up. And then another one of my favorite things to do is just to type in like and then usually some like Purdue, I see a lot. They come up with practice problems and you can get that for free and probably practice problems there. So if you need more information and stuff, you just like practice problems into the internet, you should get it. I mean, obviously those are like not us, but they're good practice. The more you read chemistry, the more you understand chemistry. Any other questions?
This connects, maybe the last thing that, we covered for later.
We start kinetics on Friday, I think. Or Monday. Let me look at the slides. Yeah, I think we start kinetics either Friday or Monday. I think you'll probably have a couple questions on kinetics for Monday, and then you'll be tested on it on Friday. But she'll make an announcement Friday of if it's what's going to be on the exam and whatnot. Some of the best chemistry is coming up. Anything else? Are you feeling better? Yes, okay. Okay, well, if there's any individual questions, it's almost 6, so I can let y'all go. And I'll see you next week. Thanks for coming.